Hey everyone, and welcome to this explainer. If you've been watching the news lately, you've probably noticed that our atmosphere has been putting on some incredibly dramatic and often scary displays. We're talking stifling, record-breaking temperatures in our cities, sudden violent storms, raging wildfires. It's a lot. But these recent global extreme weather events are actually offering us a profound, real-time lesson in atmospheric science. So today, we're going to look closely at the actual mechanics behind these events. We're going to explore the science of heat waves, how they build up, and exactly what happens when all that stored energy is finally unleashed on our environment.
Okay, let's dive into this roadmap. We've got 5 key areas to cover today. First, the anatomy of a heat dome. Second, what happens when heat meets cold. Third, the climate change connection. Fourth, ground-level impacts like wildfires and drying lands. And finally, we'll look beyond heat at super typhoons.
Starting right off with Section 1, the anatomy of a heat dome, and how atmospheric energy builds up. So, to really grasp the science of a heat wave, we have to look at where the energy actually comes from. Take the U.S. East Coast, for example. A dangerously intense heat wave recently blanketed Washington, D.C. and most of the eastern seaboard. In fact, the heat was so severe that on one Saturday, the nation's capital was reported to be among the top 1% of the hottest places on Earth. How does an entire region get trapped like that? Well, it comes down to a specific meteorological concept that weather presenter Simon King points out, the heat dome. Imagine a massive, invisible lid settling right over a city. A heat dome is essentially a large system of high pressure that develops across an area, effectively trapping stifling heat and high humidity directly beneath it. The air sinks and warms up, and because that high pressure system acts like a physical barrier, it completely prevents any cooler weather systems from moving in to bring relief.
And this brilliantly illustrates the difference between what your thermometer actually says and what your body physically feels. While actual air temperatures in cities like New York, Philadelphia, and Washington, D.C. were getting up into the dangerously hot high 30s of Celsius, the reality on the ground was so much worse. When you factor in the high humidity trapped by that heat dome, you get a significantly higher feels-like temperature. See, humidity prevents our sweat from evaporating efficiently. And since sweating is our body's primary way of cooling down, that humidity amplifies the danger exponentially. It's like walking into a steam room. To put a real number on that danger, under this recent heat dome, the Huel's-like temperature hit a staggering 46 degrees Celsius. I really want to hammer this point home. This massive number isn't just about human discomfort. It represents something fundamental about atmospheric science. High humidity means there is a vast amount of moisture, and therefore a vast amount of raw energy, being pumped directly into the atmosphere. The heat dome is quite literally acting like a giant battery, charging up the atmosphere with incredible amounts of potential energy. Moving on to Section 2, when heat meets cold, or the violent release. Think of a heat dome filled with all that humidity as a tightly loaded spring. All of that trapped energy and moisture is just sitting there waiting for a disturbance. And when that disturbance finally arrives, the results are almost never gentle. Let's walk through the precise steps of how this violent release happens. Step 1. The high humidity and heat push massive energy and moisture into the atmosphere. Step 2. A trigger arrives. In the case of the U.S. East Coast, this trigger was a cold front moving southeastward across the country. And Step 3. When that colder air crashes into all that stifling heat, the energy is violently released. The U.S. heat wave didn't just quietly fade away, it ended with an absolute big bang. Severe thunderstorms and intense lightning swept across eastern areas right through the evening and night, right in the middle of Independence Day celebrations. It was actually so severe that authorities had to order a full evacuation of the National Mall in Washington. Now, as that initial cold front pushes through, the heat gets displaced. For the U.S., temperatures in places like New York, Washington, and Philly started to drop and feel a bit more comfortable. But the heat just concentrated further down towards Virginia and the Carolinas, pushing right back into the mid to high 30s. And this exact scientific mechanism, a period of hot weather triggered by incoming colder air, is perfectly designed to create severe weather. It's the exact same clash of air masses that forms tornadoes. The atmosphere is rapidly trying to rebalance itself, instantly turning that stored heat energy into kinetic energy, wind, rain, and lightning. Which brings us to Section 3, the climate change connection, and how we're altering the baseline. Now look, heat waves and the big thunderstorms that follow them aren't inherently unusual. The US is pretty used to severe weather like this. But we need to zoom out from the immediate storms and discuss the macro science of our shifting baseline. We are seeing record-breaking temperatures in multiple locations, and that brings us to the broader climate context. According to Simon King, we know that with our changing climate, the baseline for these events is shifting in 3 very specific ways. Climate change alters heat waves by making them more intense, making them hotter, and making them more prolonged. It basically sets the scene for these exact sorts of historical records to be broken. The batteries being charged faster and to a much higher capacity than we've ever seen before.
Now, what's really interesting here is how this frames the different types of danger a heat wave can actually pose. If we shift our focus over to Europe, across France and the United Kingdom, they recently faced their third heat wave of the year. We can see the profile of their late June heat wave: extreme, record-breaking high temperatures. But the forecast for July is a bit different. The July temperatures, getting into the mid-30s, won't peak quite as high as in June. However, forecasts suggest that temperatures above 30 degrees Celsius across England could last for maybe 7 to even 10 consecutive days. This shows us that extreme danger doesn't just come from peak intense heat. It comes from prolonged duration. That's what really pushes human infrastructure and the natural environment to their absolute limits.
All right, Section 4, wildfires and drying lands, looking at the ground-level impact. Prolonged heat waves don't just make cities uncomfortable. They act as a massive catalyst for entirely different environmental disasters. To really understand this cascading effect, let's look at Greece. Now, wildfires in Greece aren't unusual, but let's break down the factors fueling the recent blazes that have hit heavily populated areas. Summers there are becoming longer. The environment is actively heating up, and as a direct result, the landscapes are severely drying out. Because the heat just continues to build up over the course of an extended season, the vegetation essentially becomes kindling. When you have a prolonged heat wave, baking a landscape that is already bone dry, you create the perfect combustible conditions for severe wildfires to ignite and spread rapidly right into populated zones. Let's move to our final section, Part 5, and see how this builds beyond heat, looking at super typhoons and extremes in the Pacific. So all this extreme energy trapped in our warming atmosphere doesn't just manifest over land masses like the US and Europe. It has a profound effect over our oceans too. Let's look at the US Pacific territories of Guam and the Northern Marianas, where residents actually had to move to emergency evacuation centers ahead of the Monday landfall of a super typhoon. Just notice the mechanics of this approaching storm. We aren't talking about a rainy afternoon. The forecasted impact includes winds barreling through at 260 kilometers an hour. When you combine that kind of extreme wind with incredibly heavy rains and massive ocean waves, you get a weather system of absolute maximum destructive potential, fueled entirely by the thermal energy stored in the ocean and atmosphere. The severity of this event is perfectly captured by this direct quote from the National Weather Service, who described the super typhoon quite simply as very dangerous. It's a blunt, stark warning from the authorities about the sheer kinetic reality of these atmospheric extremes when they finally make landfall. So the crucial point is this: whether we're looking at a stifling heat dome over Washington, D.C., a violent severe thunderstorm triggered by colliding air masses, a prolonged 10-day heat wave in the UK, dried-out landscapes fueling wildfires in Greece, or a super typhoon barreling toward Guam, it is all interconnected. It is all a real-time study in how our atmosphere builds and releases energy. As the climate changes, making these heat events more intense, hotter, and more prolonged, the baseline of our weather is fundamentally shifting everywhere. And it leaves us with a vital question to consider. As our atmosphere builds and releases increasing amounts of extreme energy, how will these cascading weather events impact your own local environment? Thank you so much for joining me for this explainer, and I encourage you to keep exploring the fascinating and sometimes formidable science of our changing world. Catch you next time.